Okay, hello everyone. So today we're going to have a look at chapter 9 in our books based on probability. Okay, so continuing on from stats that we've just finished up on, this kind of ties nicely in with our probability. So first things first, if you want to look at page 199 in your books, that's where we're starting in our books. And the first thing is what we want to do is recap over what we should already know in terms of our probability. And the first thing that we want to look at is what we call listing our outcomes. Okay, so if we have a particular trial or a particular event and we're asked to list the outcomes, we're simply given a full list of all the possible outcomes of that event. So if we take an example here, we have got our dice. Okay, so I have a dice sketch there. There's 6 sides on it. So what are the possible outcomes if I was to throw that dice? Well, the dice could potentially land on any number from 1 to 6. All right, so there are 6 possible outcomes there from throwing that dice. Okay, similarly now, if we introduced a coin, all right, what's the options, what's the outcomes when we flip our coin? Well, it's going to either land on a head or it's going to land on tails. All right, so again, we have 2 possible outcomes here in terms of flipping our coin. 6 possible outcomes when we throw our dice. All right, and that's simply it. That's listing your outcomes. That's all you have to do. One thing we may be asked is in terms of if we do 2 things together. So if we flip the coin and throw the dice, what now if we combine these 2 events? What is the total number of outcomes possible then? Well, if we have 6 outcomes originally with our dice, we have 2 outcomes originally with our coin, we simply, for the combined event, you're simply looking at multiplying the first amount of outcomes by the second number of outcomes. So we're going to get 12 outcomes for the combined event of flipping the coin and throwing the dice at the one time. Okay, if we were to list those then, all right, you'd be listing them, you'd be listing them such as, a head and a 1, a head and a 2, head and a 3, all the way on to head and a 6, tail with a 1, all the way on to tail with 3, all the way on to tail. Oh, that should be a tail. Tail, T, and all the way on to a tail and a 6. So that all now, including you would fill these in all. You wouldn't go dotting them all the way along, but that would be your 12 possible outcomes of this combined event over here. Okay, so that's simply revising what listing outcomes is. A nice and tidy way to show that is what we refer to as a two-way table. Okay, so a two-way table is nice and handy for laying out the outcomes of 2 events happening together. So I have this grid already set up based on my coin and my dice. All right, so along the vertical here, I'm going to list the possible outcomes of the coin. All right, so it is a head or a tail is my 2 options for the coin. All right, along the top, I'm going to put the various outcomes, my 6 of them, for your dice. So you're going to either get a 1, 2, 3, 4, 5, or 6. All right, and now into all of these boxes now, you're just simply filling in the combined row and column for the answer there. So if I was to get a head, all right, and a 1, a head and a 2, head and a 3, tail and a 4, tail and a 5, tail and a 6, and so on. You'd fill them all in, and it's the exact same way over here as we have done, but you're ensuring that you're not going to miss out on any potential result. So that is what we refer to as a two-way table. Okay, so it is the list of outcomes of one event on the top. So if we maybe just highlight this in a different color. All right, so this all over here on the top is your dice. all right, or event 1, all right, and we'll go for a yellow maybe, and this then is your coin, which is event 2. And the reason I have event 1 and event 2 is because they could be anything. They could be spinners, there could be anything at all in there, and you might be asked to compile and create a two-way table. But that's how it is. You look at what is the number of outcomes for one event, you list them along the left-hand side, going down. What is the list of the outcomes for the other event? You list them on the top, going across, and you're simply filling in the combined then outcome of getting this option with this. All right, so row and column all the way along, and you're filling in them all. And that's a two-way table. The last thing that we want to recap and refresh over is what we refer to as a tree diagram. All right, a tree diagram again is a nice and handy way of presenting our data. So if we take the example here of a food menu with 2 starters, 3 main courses and 2 desserts. And if we were asked to compile and draw out a tree diagram to represent this information, what does it look like? What do we do? So to start off here, right, we're going to start out here. This is event 1, right? What number of options have we? Well, we're having our starter first. So there's 2 starters, right? So 2 branches coming out from our tree. I don't know what the starter is, but that's the first starter. So this could be soup and this could be your salad or whatever it is. So you have 2 options from your starters. All right, we'll change up colors as we go actually. All right, if I picked the soup, right, as my starter, I have now how many options? I have 3 options of a main course. All right, so I've 3 options coming out here from my main course. So be it, I don't know, steak, beef, or some vegetarian meal. I have the same options again for the main course for my salad. So again, you have 3 options coming out here. All right. Now, I had the soup and I had the steak. What is my option for dessert? All right. Well, there's 2 options, so I don't know what we'll say, apple pie and chocolate brownie or something. So you have 2 options now here. No matter what main course, you still have 2 options coming out for your dessert, regardless of which of your main courses you selected. Okay, so this is, I've actually forgot, I'll go back in there, but this is your dessert here, coming down in blue. I have the starters there. Go back to orange here for your mains. So these are your mains. Now, the last thing that we need to do is we need to include here the probability of each. So if we come back here to our starters, there was 2 starters, all right? So the probability that I'm going to pick, I have to eat a starter. So say you're going in and it's a set price for a 3-course meal. I'm going to have a starter, I'm going to have a main, and I'm going to have a dessert. I've only 2 choices to pick from. So I have to pick one or the other. So what is the probability or the percentage chance that I'm going to pick the soup or the salad? Well, it is a half. And a half. So I'm going to, these are my only options, so I'm going to have to pick one out of the 2 and one out of the 2 here. If I look at my main course, you know, there's only 3 of them and I have to pick one, so the probability is a third, a third, and a third, and similarly down here, your third, a third, and a third. And again, when we come to our desserts, there is 2 options, so I have a 50-50 chance of picking either of my 2. Now, again, I'm gone kind of small in here. If you were in your copies, you'd be a bit neater than this. That's a 3, 2. Okay, so again, I would go a lot larger when you're doing your tree diagram. Space is your friend here, and I suppose I really should have gone a lot bigger than in this when I was actually doing it in this demo, but we'll work with what we have. All right, and so say that's first of all, that is your tree diagram complete. All right, so you have a tree diagram outlining the selection of a 3-course meal where you have 2 starters, 3 mains, and 2 desserts. Now, if we were to throw back this question up here, list and outcomes, how many possible outcomes is there? So I'm going into this restaurant, how many different possible combinations of meals could I have? Right? Well, we'll just go to a different color here. We'll go to white. So I'm going to use white in a while. So there are 2 possible outcomes with my starters. Right? Remember, when we've got more than one event, we multiply the outcomes by each other. So multiplying the outcomes, well, I have 3 options for my mains, and I have 2 options for my dessert. So 3 by 2 is 6, 6 by 2 is 12. So there's a total of 12, where am I here now? I'll get rid of that. All right, so there is a total of 12 combinations in here with this. So say if I got the soup, I could get the soup, the steak, and the brownie. Or I could get the soup, the steak, and what should we say, the apple pie. All right. Or I could have gone for the salad and the steak and the brownie. All right. So you've got 2 options with your starter. You have 3 options, should I say, with your main course, and 2 options with your dessert. So you have a total of 12 possible outcomes here within this menu. All right, so that's the revision of listing your outcomes, your 2-way tables, and your tree diagrams. And the first set of exercises here is a nice and straightforward, easy enough questions there, starting on page 201. So we'll look at exercise 9.1, and we're looking at questions 1 to, I think, isn't it 11? Check. Yeah, 1 to 11. Okay, so that's your first exercise there. The next one we want to look at now, again, it's going to be for the first day here today, is what we're talking about in terms of our chance and our probability scale. So pause the video now and I'll just get this page open. Okay, so this is the next section we want to look at, and we refer to it as our probability scale. So chance and the probability scale. So in this chapter, terminology and our words, we need to pay very close attention to what is it being asked of us, what and how is the question phrased, and that will really dictate how we go about getting our answer and all that. So pay attention to the English statement that's asked of you. So if we just, we'll skip this, we'll come back to it in a second. So if we just look at our scale here, all right, so it ranges from 0 all the way to 1, all right, or if we were to look at that in terms of percentage, we're at 0% all the way up to 100%, all right. So when we're talking about an event happening, all right, the event either happens, which is up here at 100%, so it's certain to happen, all right, or the event doesn't happen or can't happen at all, which we say there's a 0% chance of it happening, so then that is impossible, all right. So if we were to consider, say, what is the percentage chance that you're going to win the lotto when you buy a ticket, all right, well, you're going to say, well, it's probably down here in the unlikely region here, so your fair low chance, the probability is very, very low. But if we said to change the question, said, what is the probability that you're going to win the lotto if you do not buy a ticket? Well, you can't win the lotto without a ticket, so then you have 0% chance of winning. It's impossible. It's impossible to win if you don't have a ticket. All right. If you could read the future and you could say, well, I know the numbers that are going to come up, I'm going to do my lotto ticket and select the numbers that I know are going to come up, then there's a certain, I'm guaranteed to win there. All right. Anywhere between that we refer to as different words in such as even chance, likely, certain, unlikely. So if we look at our unlikely and likely, all right, where they are in terms of your probability or your percentage, all right, unlikely is anything less than 50%. All right, so it's less than our 50% there. Anything on the right hand side of 50% all the way up to say 99%, we define that in with the English word of likely. So if it's less than a 50% chance of it happening, we say it's unlikely to happen because something else is more likely to happen than it. If we say that the percentage of the event happening is over 50%, then it is more likely to happen than not. Okay, so that's just in terms of the English there. All right, and you can read that up there yourselves in your own time. I'm not going to go through that. That's kind of that pretty much explained there. All right, so, and even just if you look, it's impossible to get a 7 when a normal dice is rolled because a dice only goes up to as far as 6. Okay, so the next group of questions there I want you to have a look at there is your exercise 9.2, having a look at question 1 to 6. Okay, so that is for your first evening's work, both section 9.1 and 9.2. So pause the video there now and go ahead and do those two. Okay. Okay, so the next thing we want to look at is equally likely outcomes and talking about probability and also bringing in the words even chance. Okay, so when you hear the word equally likely and also the word even, it can be very easy to kind of confuse the two of those in what they mean and how they apply to probability. So before we get to those, we'll just have a quick scoot through this and read this in terms of what we've just previously looked at. So before you can start a certain game, you must throw a dice and get a 6. So that particular activity there is what we call a trial. All right, you're throwing the dice and you're trying to get a 6 to get into the game. So that's your trial. So the trial is throwing the dice. The outcomes that could occur are all the numbers of 1 to 6 for a fair dice. Okay, so you're conducting a trial of throwing the dice. The outcomes is 1 to 6. The sample space is the list of outcomes. So the only possible outcomes we refer to that as that's the sample space of the experiment, all right, or the trial. When we get what we want, right, we call that an event. All right, so say what is the probability of rolling a 6 when we throw a fair dice? Well, there's 6 options there and we only want one of the 6, so we have a 1 in 6 chance of landing on a 6. Okay, so that's the event. If we require an even number when throwing a dice, then the events are favorable outcomes are the numbers 2, 4 and 6. So that's just, you're just listing what you want to happen. So what is the event that you want to happen? All right, and remember probability for anything here, so this is good to take down your copy. So probability and I always just refer to it as P in short. So the probability P, and we'll actually move over here. So the probability of any event P is equal to, and we're creating a fraction here, what we want all over what can come up. Okay, so for the example of the dice here, well, we want a 6. How many 6s is there on the dice? Well, there's only 1. How many possible outcomes is there? What could come up as our answer? Well, there's any number from 1 to 6, so there's 6 possible outcomes. So the probability that we throw the dice and we land on a 6 is 1 in 6. Okay. Now, if we look at equally likely and even, all right. So if we look at this dice, or this spinner here, should I say, you've got your red and your blue. There's 3 reds, there's 3 blues. All right, we spin the spinner. What color lands on the arrow? Well, each color there, your blue and your red, is equally likely to land on the spinner as the other. Okay, because there's the exact same amount of red compared to blue sections in this circle. So this event or this trial, the results or the outcomes are equally likely. So they're equal to each other. If we compare it to this one here, where we've got your red, your yellow, and now, but blue here, in effect, there's two blues. Okay, if we look at the probability, right, well, of the whole thing here, there's a probability of 100%. How much of that figure is covered by blue? Well, by dividing this into 2 quarters, we can see, well, we've a 2 in 4 chance of landing on a blue, which is a half or 50%. All right, so we've a 50% chance of landing on a blue. All right, if we remember back here, so if I just turn this layer off and we go back to this, our probability scale, anything that has a probability of 50%, we say that it has an even chance, okay, of occurring. So a 50% probability, the English word that goes along with that is even. So we have an even chance of landing on a blue in the example back here. So we have an even chance here of landing on that blue. Should I turn that off? So we have an even chance of landing on a blue because the probability of blue coming up in this spinner is 50%. So an even event has a probability of 50%, whereas an equally likely, they have percentages that are equal to each other. Okay, so be careful in your English there, even and equally likely outcomes or events. All right, down here, probability here of any event, E, is equal to the number of favorable outcomes over the possible number of outcomes, or in simpler English, what you want all over what can come up. Okay, so with that being said, we're going to have a look at a few more questions then. So I'll just yellow to highlight it. So we're going to have a look here then at exercise then 9.3, and we're going to have a look, now there's a lot of questions here, question 1 to 21 here, but we're only going to look at the odd ones. Now, if you're finding these a little bit tricky to get your head around, I would suggest doing all of them, okay, rather than just the odd ones. More, as remember the phrase, practice makes perfect. So the more you do, the better you're going to be at them. So for some students, probability can be an awful one to get your head around. It's a tricky one to get your head around if you don't understand it. All right, so practice makes perfect. I'm only asking you to do the odd ones. Feel free yourself to do them all if you feel it's necessary. Okay. Okay, so on to our next section here, where we're looking at 2 events happening at the same time. So we've kind of looked at that at the very start, and using our sample space or our two-way table or tree diagrams here to help us out. So if we just have a look at the example that's in our book here, and I'm going to go through and we'll do question 2 with you here on this. All right, a two-way table or a tree diagram, they're very useful for combined events, all right, or 2 events happening at the one stage. So if we look at here, so 2 dice are thrown and the scores are added together. Set out below is our sample space given all the possible outcomes. So if we look in here, all right, on our blue dice, we throw it, we can get all the various outcomes from 1 to 6. On our green dice, we can throw and we'll get all the various outcomes from 1 to 6 also. All right, we might be asked here, work out the probability that the total is exactly 7. Well, within here, within our sample space, so this is our sample space, this is the total number of outcomes that we can have by throwing these 2 dice. How many times is 7 recorded? What is the frequency of a 7 coming up when you're combining the results of the two dice? Well, you can see here, counting them up here, we have 6 7s. What is the total number of outcomes? 6 multiplied by 6, 36 outcomes. So that simplifies to be a 1 in 6 chance of getting a combined score of 7 when you're throwing the two dice. What about part 3? The total is 11 or more. So how many times do we record in here a combined score of 11 or more? Well, there's only 3 of them. All right. So there's 3 out of a total possible 36 outcomes. That simplifies to be a 1 in 12. All right. And that's pretty much it. Our job generally will be to draw out a two-way table to represent the results. So if we look at, say, question 2 here, we've got 2 spinners and the 2 of them have the numbers all from 1 all the way up to 4. We have to create, well, it's given to us in this case, but a lot of the time you'll have to create your two-way table. So one event, the second event, and within here you're including here your sample space or the total number of outcomes. And in this case, again, they're adding the results. So 1 and 1 on both spinners results in a 2. A 3 from the green spinner and a 1 on the blue spinner. 3 plus 1 is 4, and so on. And then you're just asking, or they're asking you questions based on that. So the total score is 7 or more. Again, count within in your sample space the frequency of getting 7 or more. Well, there's 3 of them. How many possible outcomes have we? 4 multiplied by 4 is 16. So 16 all over, or sorry, 3 all over 16, and simplify then as much as possible. And that's pretty much your sample space in terms of your frequency table. If we look over onto the next ones, that's pretty much all frequency tables again, or not frequency table, but two-way tables. Okay. So what I want you to do here now is these exercises from 1 all the way up to 9 based on 2 events happening and either drawing a tree diagram or a two-way table. Okay, so that's again just practicing your two-way tables and your tree diagrams in relation to 2 events happening at the one time. Okay, so trusting you've paused the video and you've gone off and you've done that, we'll fly on now to our next section. So we're estimating probabilities based on an experiment. Okay, so a lot of probability, you're conducting a trial or an experiment. All right, so if we throw a dice, what number does it land on? Does it land on a 4? Does it land on a 5? We're just recording that down and we're going to work out then the probability, maybe identifying is the dice fair or is it unfair. So if we just look down here at this table they've included in the book, all right, they've flipped a dice, all right, or sorry, a coin here. So number of tosses, number of heads is all that we're given. We're not told anything about the tails. So after 10 times tossing the coin, we have ended up getting 6 heads. All right. So what is the probability after 10 tosses of the coin of getting a head? Well, it is, if I copy this, we'll bring it into the, and I can do a bit of work on it. Okay, so we have 6 heads, all right, out of a total of 10 tosses, all right, so that is equal to 0.6 or 60%. All right, so 60% of the head tosses here, or the total tosses, should I say, resulted in a head. And you can see just heads divided by the number of tosses. All right, so the number of heads divided by the number of tosses. If we look at our percentage going down, all right, what you would expect from a fair coin is a 50-50 split between your heads and your tails. And if we look at here, because we have only 10 results, we're up here at 60%. So you may be arguing the fact that this coin might be biased, but we've only experimented 10 times. If we experiment 100 times, see how we're a lot closer to 50%. And the greater that you go in terms of the number of trials in your experiment, the more accurate our results are becoming. All right. So anytime you're conducting an experiment, the greater number of trials that you include in that experiment, the more accurate your results are going to be. Okay, so that's one thing to pay attention to in terms of your experiments. The more experiments you do, or more trials you do in the experiment, the more accurate your results are going to be. Now, that brings us on to our next section here, which is to do with frequency tables. So, okay, so here we have a lad, Derek, and he was outside his school and he recorded the colours of the cars passing. All right, he had a tally done up for when he was recording them, and he then filled in the frequency afterwards. All right, what we can do here, and what we've seen already when we were looking at our statistics, is we can create what we refer to as a relative frequency table, okay, where we're talking about probability of these various colours passing. Okay, so basically what we're doing here in terms of a relative frequency table is we want to, first of all, we want to find, well, what is the total number of cars recorded? So how many cars passed the gate, all right? And if we add up all of these numbers, we would find that there was 100 cars passed. So there's a total of 100 cars in Derek's experiment, all right? Now, we can work out then the relative frequency. So I'm just putting RF for short. So relative frequency of each particular colour passing. All right. So relative frequency, you're simply putting the frequency of the event over the total. So you're putting your frequency all over the total, so of trials or data entry points here. So if we look at the white car, there was 24 white cars had passed out of a total of 100 cars. So you've got 24 all over 100, which is 0.24%, or if you want in terms of percentage, it's 24%. All right. If we looked at the green cars, well, it's 10 all over a total of 100, which will be 0.1 or 10%. Okay, and you would do that for all of these in here. All right, and what you would find is all your percentages would add up to 100%. All right, now by including that, this is very, very useful in terms of working out and being asked. If I ask the question here to Derek, all right, another car now has passed that road, what is the probability, or what do you, from your trial and your experiment here, what is the percentage that the next car that's going to pass will be a white car? Well, he could look at his results and he could say, well, I estimate that the next car that's going to pass the road will be white 24% of the time. Or if I asked him, well, what's the probability that a green car will be the next car that will pass? Well, he could say, well, I estimate that the green car will pass next 10% of the time. So we can use a frequency table where we've conducted an experiment, a trial, we've recorded the results. You can work out what we refer to as a relative frequency, or which is basically probability of that event happening. Okay, which I find and I think is quite useful there. So if we look at here, the various questions that Derek has been asked. So what is the relative frequency of blue cars? All right, well, blue is 16 all over 100, which is 16%. And as I said, you can go on and estimate future events happening based on a trial that you have done. And that's leading us into the next section, what we would refer to as expected frequency. So that's predicting what might happen next based on a trial or experiment that you have done would tie into what we call expected frequency. So if we just consider this bag of marbles, all right, there is 5 red marbles and 3 blue for a total of 8. So if we were to put our hand in, pull out a single marble and record the result, put that marble back into the bag after you've recorded, and we were to do that experiment 400 times, all right, how many would you expect to be blue? All right, so how many marbles, if we were to pick in and out of that bag 400 times, writing down the result each time, how many of those 400 trials would you expect that we would record a blue marble? Well, you look at what is the total. There's a total of 8 marbles in the bag. There is a total of 3 blue marbles. So what is the probability of picking one blue just once? Well, it is the probability of what you want, which is a blue one, which is 3, all over the probability of what can come up, which is any one of the 8. So you have a 3 in 8 chance of picking a blue marble, and we're conducting that experiment 400 times. We're going to then, that simplifies or works out to be 150. So we're going to expect 150 of the marbles that we pull out to be blue. And that is what we refer to as expected frequency there. Okay. If we just look at this here, so sometimes you can be given the probabilities here and one left out. Well, we know, looking back at our scale ranges from 0% all the way up to 100% or 0 to 1. So if we add all of these numbers, the difference in the combined result here and 1 is equal to the probability of landing on a 5 on this spinner. So they've worked it out to be 0.15. Okay, so that is the probability of working out that, and then there's various other questions asked. So say if here we look at part 3, if a spinner is spun 200 times, how many times would you expect it to land on a 3? Well, we need to look at, well, what is the probability of getting 1 3? It is 25% or 0.25. So you're going to multiply your 0.25 by the number of trials, which is 200 trials. So you're going to expect 50 of those to be the number 3. And that's basically your expected frequency. All right. So what do we have a look at here in this section? We had a look at experiments, and we figured out that the greater number of trials in an experiment, the more accurate our results were. We remembered back to our frequency table, and we said we could add in another section here in terms of a relative frequency, which we refer to as our probability, and we can use that to work out the probability of a particular event happening, or we can use it to predict a future event for occurring. And we also looked at expected frequency in terms of conducting a trial a number of times. What would we expect as our result? So out of that section there, we're going to now have a look at our exercise 9.5, and we're going to go ahead and do questions 1 to, how many of them here? Yeah. So we're going to have a look at questions 1 to 15 there. Okay. Pause the video there and you can go off ahead and do those. Okay. So the second last section that we want to look at is when we're combining our sets and probability. Okay, now if we think back when we were talking about probability, we said it is, creating a fraction, we're looking at what we want on the top all over what can come up in the bottom. All right, so it's always important first of all to start out and get, well, what is the total number of outcomes that can happen? All right, so if we look down here, there's 130 different outcomes that could happen here. So members of a football club, so 40 are members of some sport, right? 40 of them play football only, 35 play tennis only, 10 play both football and tennis, and 45 play neither. So 40 and 10 is 50, 50 and 80 is 130. So there's 130 possible outcomes here. And we're asked, well, say, what is the probability that a player picked at random does both football and tennis? Well, there is 10 that do football and tennis. So the probability that they do football and tennis is 10 all over the 130. And you'd simplify that. Same thing, 40 all over 130 for football only, and so on. So you're just looking, the main thing to get when you're talking about sets is to get the overall number of outcomes of the event. All right. So if you have a look at any of these, indeed, including 3 sets here, again, we need to make sure we get the total number. All right. So if we have a look at here in the given Venn diagram here, your universal set represents the houses on a given street. C represents those which have a cat. D, which have a dog. And if a household is selected at random, what is the probability that that house has a cat? All right. Well, what is the total number of households on the street? You're going to add up these 4 numbers together. All right. So you're getting your 26, should I say, and 14 there together is 40, 52, 82. So there's a total of 82 people on that street. 14 and 12, right? So in terms of a cat, 14 have a cat only. 12 have a cat and a dog. But these 12, just because they have a dog, they still have a cat. So there's a total of 26 cats on the street. So 26 all over 82, and simplify, and that's your probability. A cat and a dog, 12 all over your, 82, and again, simplify. So the main thing when we're talking about probability in terms of sets is to get the overall number of outcomes possible. Sometimes you might have to work out, say, the same as when we're looking at sets, to work out the number in a given region. So here we're told a group of 50 students. Well, your universal set is 50. So all our regions in here have to add to 50. So we have 38 out of the 50. So the x has to be 12. All right. So that's those. So if you take and you just have a go at question 1 to 7 there now. And that's then going to, you can pause the video then while you're doing those. Then we're going to move on to our tree diagrams, and we're brought in 3 events rather than 2 events. So we've mainly been looking at tree diagrams in terms of 2 events. Now we're bringing in 3 events. I done this in the introduction of this section here anyways, but you're filling in your probability. All right. I didn't work through getting the probability of a particular event happening. So if we have a look at this example here, should I say, right? We've got 2 spinners, 2 colours, right? Make one of your tree diagram branches for the first spinner. Make your next for the second spinner. So you decide. So if this is spinner A, this is for spinner A. There's 2 possible outcomes, red or blue. So if you have a red or a blue, if it landed on red, and we then spin the second spinner, what are my outcomes or options here for the result of this? Well, again, it is a red or a blue. So again, red or a blue. And the same thing if I landed on blue the first time and I spun the second one, well, again, I'm going to get either a red or blue for your second spinner. We then infill our probability for the first spinner of landing either on a red or a blue. Well, if there's 4 possible outcomes, 3 of those are blue, we have a 3 in 4 chance of landing on blue, and conversely a 1 in 4 chance of landing in a red. And if we look, we're going to spin that spinner, it's going to land on either red or blue. So there's a 100% chance, or 4/4 probability of landing on a colour. So the quarter and the 3/4 add to give 4/4 or 100%. Same, we want to fill in now the probability of along each tree here for each of your red and your blue for spinner B. So we have 5 divisions in here. 3 of them out of the 5 are for red. So 3/5 for red, 2/5 for blue. 3/5 for red, 2/5 for blue. Now, that's your tree diagram filled in. Next, you'll have to answer various questions on it. So what is the probability that I spin the 2 spinners and I get a blue and a blue. Well, it is 3/4 multiplied by 2/5. So I have a 6 in 20 chance, or 3 in 10, or 30% chance of spinning these two spinners and getting two blues. What is the probability of getting two reds? Well, it is 1/4 multiplied by 3/5. So it is 1/4 multiplied by 3/5, which is 3 in 20, or 1.5 in 10. So you have a 15% chance here of getting two reds. What about a red and a blue, or a blue and a red? Same idea here. Okay, so exercise 9.7 there is all based on your two-way table, or your tree diagram, should I say, generally with two or more events. Okay, so that's the last section there, and finally before you test yourself. So have a go from 1 to 9 there on those, and that is the finish of this chapter here, the overview. Obviously we'll do a little bit more in depth in some of our live classes, but that's just an overview of me talking through each of the particular sections for you. Okay, best of luck, and we'll see you again.